Hi everyone, and welcome to more Wet Rock and Chocolate Milk. This is the Pet Peeve series where we talk about scuba science in way too much detail. This series is for all y'all people out there with a scientific background who, like me, are a bit annoyed by the oversimplifications used in the dive industry and who are not afraid of scuba science in gory detail. Today, we'll break down how real gases behave under pressure and see when it actually matters to look Mother Nature a little deeper under the hood. To do so, we'll start off by looking at the ideal gas law and how it's being applied in the dive industry. Then, we'll have a look at van der Waals correction and look at some visualizations of the difference between the ideal gas law and van der Waals. This will bring us to some scenarios in diving that we can have a look at to see whether or not we actually need to care about van der Waals correction to the ideal gas law. So, to get things started, what is the ideal gas law? Well, it's usually written in the form PV is equal to nRT, so the pressure times the volume is equal to the number of particles times the gas constant times the temperature. Here, in order for us to use units that are particularly useful in diving, we're going to be looking at pressure in bar, volume in liters, number of particles in mole, the ideal gas constant in whatever is reasonable, and the temperature in Kelvin. So, what is the ideal gas constant? Well, it is nothing other than the Boltzmann constant times Avogadro's constant. So, in units that we like to work with, that is bar liter per mole Kelvin, it is whatever this number here is. And for most of what we're going to be looking at, this works out quite nicely. If we keep the temperature constant, then what we have is a relationship between the number of particles, the volume, and the pressure. Similarly, if we keep the volume constant, then we have a relationship between pressure and temperature. But realistically, what we really care about is the density of particles. So what we're going to be looking at is mainly the number of particles per liter in order to make our visualizations. So let's have our first visualization here. If we take the density of particles and we vary it, and we look at the pressure at different temperatures, then we get a fun little linear plot, all fine at different temperatures. And this is where most of the laws that we use in diving come from. If you put more gas in, you have a higher pressure. If you have hot gases, then the pressure is higher than if you have cold gases. So if you're having a hot fill, that's bad because it'll cool down, and even though the pressure says that you're fairly high, when you're filling it, when you're actually going diving, it's going to be less. So how do we actually use all of this? Well, we can use it in order to compute the available gas. Say we have a 12-liter cylinder, we charge it to 200 bar, then we have 2,400 bar liters of gas available. We also use it to compute any consumption rate. So let's say we have a 20 liter per minute sac rate, and we're doing a dive at 20 meters, so at 3 bar, then really what we're saying is that we're having a 60 liter per minute gas usage, although the more accurate version of this would be to have 60 bar liters per minute, because well, the available gas is also given in bar liters. So if we're going to take our 2,400 bar liters, we divide it by 60 bar liters per minute, then we get a runtime of that cylinder in minutes. Also, though not quite as quantitative, we do use it to justify temperature dependence of cylinder pressure, which leads into the already mentioned hot fills, but also into effects like cooling off when jumping into the water. So if we're diving on a hot summer day, let's say it's 30 degrees out there, maybe even hotter because the cylinder is lying in the sun, and then we jump into a fresh 20 degrees water temperature, we're going to have quite a bit of a drop in pressure relatively early on, not just because we start breathing off the cylinder, but also because the gas in the cylinder is cooling down, lowering the pressure. And the ideal gas law allows us to predict how that happens, although we rarely do that calculation, if ever. Now, what's wrong with the ideal gas law? Well, there are a couple of assumptions that the ideal gas law makes. One of them is that our particles have no actual size. But as we put particles under lots and lots of pressure, then they can start bumping into each other. And so the actual size of the molecules or particles matters once the pressure becomes high enough. The other main assumption that we have is that our gases don't actually interact physically with other particles in the same gas. And this may or may not be true depending on the gas that we have, but if we're looking at molecules, then the distribution of electrons in the molecule will actually have an impact, and this is very important for why water is liquid, for example. So, Van der Waals says we need to make some corrections to the ideal gas law, and this will have an impact depending on the gases that we use and the pressures that we're using them at. So, taking the P is equal to density RT, Van der Waals says we need two correction terms. First, we need a quadratic term on the density to the pressure, and then we multiply all of this with a linear term, depending on the density. And the two constants that we have here, A and B, they will depend on the gas that we're breathing, or that we have in our cylinder. So for oxygen, A is about 1.382 and B is about 0.03186. Nitrogen, very similar values. Helium, significantly smaller values. And this fundamentally boils down to the fact that, well, nitrogen and oxygen come in molecules, so they have a much bigger size, but they also have a lot more electrons floating around, which can affect the intermolecular forces much more than helium will have. So, if this is the case, well, we sometimes dive with oxygen. We don't really dive with nitrogen or helium. I mean, we put it in the mix if we're talking about trimix or nitrox or just air diving, but realistically, most of the gases that we have will not be one of these three. So the first thing that we need to do is we need to find these A and B values for any given gas that we actually have in the cylinder. To do so, Van der Waals also gave us some formulas, which says the A value is computed given the A values of the different gases that are in the mix and the fraction of the various gases that are in the mix. And then we have this weird averaging where we take products of the different gases, A values, and take the square root of that, and we average weighting by the fractions that are also multiplied for some reason that we don't need to go into. Now, the B values are very same formula, just A's replaced by B's. And that means if we are actually looking at something like air, we can now compute our A and B values for air, which are, well, our fractions being 21% oxygen, 79% nitrogen. So we'll take this double sum where we start with the two oxygen indices, so that is the A for oxygen multiplied by the A for oxygen, so A for oxygen squared. Take the square root, so it's just the A for oxygen, times the fraction 0.21 squared. Then we have two terms where we have the A for oxygen and the A for nitrogen. That gives us the 1.382 times 1.370. Take the square root of that, multiply with the two fractions, 21 and 79%, and 2, because it once comes for I being oxygen and once for J being oxygen. And then finally, A and J both being nitrogen, we get a similar term to the oxygen term, so we take the A value for nitrogen, square it because it comes twice, and take the square root, so it's just the A value for nitrogen, and then we multiply this by the 0.79 square as well. And if we plug this into our favorite calculator, we come up with a number that is about 1.373. Do the same game, but with the B values for oxygen and nitrogen, and we get a B value for air that is about 0.03721. And that is what we're going to be using in van der Waals equation instead of the ideal gas law. So, how much of an effect does this actually have? Well, let's plot the two predictions. Here we have the ideal gas law plotted and van der Waals prediction for the pressure as a function of the gas density. Now I've chosen to have this at 16 degrees Celsius because I think that is a fairly reasonable assumption of some representative temperatures at which we might be diving, but similar things will happen at other temperatures. Now, what do we see? Well, in the low density region, i.e., the low pressure region, the two pretty much give the same value, and that's not overly surprising given that van der Waals changes are about corrections when you have lots of particles in a small space, so when we're talking about high densities. But as we go into the, well, about 70 to maybe 230 range, we can see that the van der Waals pressure prediction is actually a little bit lower than the ideal gas law prediction. That's interesting as this is a pretty decent range of where we're actually diving. So we're going to be talking about this one a little bit later. What's next? Well, there comes the point where the two give the same prediction for air, and that point's going to vary by temperature, but something interesting would be to actually calculate where that is. And once we go beyond that, we fairly quickly see discrepancies in the two predictions, which really shows that above something like 230-ish bar for air, well, there is quite an effect of the particle sizes. So if we're talking about 300 bar cylinders, then the pressure prediction is quite different. And so this is again something that we may want to look at. But first, let's have a look at the relative effect of the false prediction or less accurate prediction that the ideal gas law gives us when we normalize it on pressure versus van der Waals. Well, at 0 bar, the two coincide. At, well, somewhere around, well, this looks more like 225 now, bar, they also coincide. And in between, in the 100 something, 2025-ish region, we overestimate the gas that we have, or the pressure that we have, by about 6%. Beyond the, well, 225-ish, we can go down to a over or underestimate by about 92% of the pressure if we're using the ideal gas law. So, what does all of that mean? Well, first of all, where's the point where the two coincide? That point can be computed by taking van der Waals equation for the pressure and setting it equal to the ideal gas law, which gives us an equation in terms of temperature for the gas density. And if we plug that back in to van der Waals or the ideal law, then we get an equation in terms of temperature of the point where the two gases coincide. And obviously these numbers are for air particularly. If we have different gases, then we're going to have different numbers here. But if we look at the range at 4 degrees Celsius, it's 232 bar. Funny number. At 10 degrees, it's 229, 16, 225, 22, 221 bar, and at 28, 216. Sure, we can be diving at a little bit higher than 28 degrees Celsius, but once we jump into the water, doubt that we're going to have much more than 28 degrees Celsius. And given that water freezes at 0 degrees Celsius, we're not going to go much below 4 degrees Celsius either. So for air, the range that we're looking at is roughly where we have a full cylinder, at least a full 232 bar cylinder. we're going to be talking about 300 bar cylinders a little bit later. But first off, if we're below that, that will be most of our diving, then we saw that the ideal gas law overestimates the pressure that we have in a cylinder given a certain number of particles. But if the pressure given a certain number of particles is being overestimated, then that means if we're reading a pressure and we're trying to convert this into gas available, we're actually underestimating how much gas we have. So the ideal gas law gives us an underestimate, and by how much is that? Well, if we look at a 12-liter cylinder, we charge it to 210 bar, we're at 20 meters and we're breathing with a sac rate of 20 liters per minute, then we can do the calculation. 12 liters by 210 bar gives us something in bar liters. The 3 bar times the 20 liters per minute gives us 60 bar liters per minute. So if we divide the 12 times 210 bar liter by the 60 bar liter that we're breathing, we will see with the ideal gas law that this cylinder will last us for 42 minutes until it's fully empty. But if we use van der Waals, then what we really need to look at is the number of particles that we have in the cylinder. So using van der Waals equation for a 12-liter cylinder, 210 bar, and we're taking our 16 degrees Celsius for our calculation, then we see that there's actually 106 moles of air in the cylinder. Similarly, if we're taking 20 liters at 3 bar, then that is 2.5 moles using van der Waals, and therefore what we're having is a consumption of 2.5 moles per minute out of the 106 moles that we have total available. So the actual cylinder lasts us 42.4 minutes. And this is what we've seen. It is a little bit underestimating using the ideal gas law, and it's not that bad, right? This is like 1% roughly of the actual cylinder size or of the prediction. Depth variation, a little bit of working harder, slower is going to have way more of an impact than whatever this difference is. Therefore, for such a computation, we really don't need to care about the ideal gas law versus van der Waals. If, on the other hand, we look at a pressure above that equal pressure point, then the ideal gas law underestimates the pressure that we actually have, which means it overestimates the amount of gas that we have available. If we're reading the pressure and we're figuring out how much gas we have. Now, a common 300 bar cylinder would be a 7 liter. So if we take a 7 liter on a 20 meter dive and 20 liter per minute sac rate, then the ideal gas law, same computation, 300 bar, 7 liters gives us 2,100 bar liters. We still have 60 bar liters per minute of consumption. So 2,100 divided by 60 gives us 35 minutes of actual runtime on the cylinder. If we use van der Waals instead, then the 7-liter cylinder at 300 bar will give us 80.2 moles of air in the cylinder. We still have the 2.5 mole per minute consumption rate, so it actually only lasts us 32.1 minutes. And this is roughly 10%. Now, this actually starts becoming interesting and something that we want to think about. In particular, since it is actually shorter than we think with the ideal gas law. So, what does that mean in relatable terms? Well, if we take our 7 liter at 300 bar and we convert it to a 200 bar cylinder, how big would that cylinder be so that it has the same amount of gas? Well, using van der Waals, it is a 9.6 liter cylinder. But using the ideal gas law, then our 2,100 bar liters divided by 200 bar would give us a 10.5 liter cylinder, which is significantly more than the 9.6 that we actually have as a comparable cylinder size. In fact, we only have about 91.4% of the gas available to the ideal prediction, which can become quite interesting for actual dives. Because if we start thinking about a dive in which we have to perform some task and we do our gas calculation based on this is what we need to do, this is how long it's going to take, so therefore we need this and this much gas. So the best cylinders that we can use is a 300 bar 7. Well, the ideal gas law is going to tell us something that is a little bit too small. And if we were to actually then execute the dive, we might end up in the situation where we're almost done with the task and now have to make a choice. Do we end the dive as we should because we've reached our reserve gas and do another dive to finish off the job? Or, let's face it, if there's only a small bit left, a lot of us will be thinking about, let's just get this done and go a little bit into our reserve. But obviously, that's very, very dangerous, and nobody should be advocating for doing anything like that. So, here it becomes interesting and important to think about van der Waals. More important, even, is if we're talking about gas blending. Let's say we want to make a 100-meter dive. It's going to be a rebreather dive because who does this on open circuit? So we're going to have to choose a diluent gas, and I'm going to say we're going to be looking at a PO2 of 1.1 so that we can dilute actually what's in the loop. And I don't want to have an equivalent narcotic depth of deeper than 25 meters. My cylinder is going to be charged to 232 bar, and I'm going to be keeping to the 16 degrees Celsius. So, what gas do we need? Well, 100 meters is a pressure of 11 bar, so the PO2 of 1.1 means that we need 10% of oxygen in the mix. Our END of 25 meters is 3.5 bar, but the partial pressure of nitrogen is only 79% of that because it's equivalent air depth. So we're looking for a PN2 of 3.5 times 0.79. And if we divide that by our 11 bar ambient pressure, that means that we need 25% of nitrogen in the mix. And the rest, i.e., whatever 100 minus 10, so 90, minus 25, 65%, that's going to be helium. So we're going to be diving a Trimix 1065 on this dive. Now, what does that mean for our blending? Well, first and foremost, we need to compute what our A and B values are for this Trimix 1065. Plugging in the numbers just like we did with the air calculation, except now we have 3 terms, so there's 9 values that we need to sum up, gives us an A of 0.28205 and a B value of 0.027992. With that, we can now solve van der Waals' equation for the density of particles in our cylinder at 232 bar and 16 degrees Celsius. Well, if we do so, we will find that we actually have 8.062 mole per liter of Trimix 1065 in the final mix. This needs to be split between the gases. So 1065, 65% of these 8.062 mole are helium. So 8.062 times 0.65 is 5.240 moles per liter of helium. Then 25% is going to be nitrogen. So we're looking at 8.062 times 0.25. But we're not going to be filling pure nitrogen, we're going to be filling air. So we're not filling at 100%, we're only filling at 0.79 fraction, meaning that to get our 8.062 times 0.25 number moles per liter of nitrogen into the mix, we need about 2.551 moles per liter of air to be filled in the cylinder. And the rest, which is 8.062 times 0.1, is to be filled up with oxygen, But we've already put some oxygen into the mix because we've filled with air here. So we don't need the full 8.062 times 0.1 because we've already filled 8.062 points 0.25 divided by 0.79 times the fraction 0.21 much oxygen through the air fill. And if we put this into our calculator, that is 0.270 moles per liter. And we can check that 0.270 plus 2.551 plus 5.240 is 8.062, except it isn't quite because rounding errors. But at the end of the day, it doesn't really matter too much. So we now have the number of moles that we need to fill into our cylinders. Well, we're not filling by counting molecules, we're filling by looking at pressure. So we need to turn this into actual fill pressures. And that means we need to pick which one we're going to fill first. Let's say we're going to fill the helium first. So to fill our 5.240 moles per liter of helium, we need to fill the cylinder to a pressure of 143 bar. Now, if we cross-check this against the 232 that we're trying to fill to, 143 is only 61.6% of the total pressure that we want to achieve. The ideal gas law would say that we need to fill 65%. So this is a 4% difference in fill pressure that we're looking at. And if we weren't taking van der Waals into account here, that would already be noticeable. Now, would I care if I asked for a 1065 and I got something like a 1069? Well, it's going to put my END to even lower than 25 meters. So personally, I wouldn't really mind too much. But realistically, I also wouldn't pay for the additional helium if I'm asking for a 1065. I'm going to be paying for a 1065. If you're giving me more than that in helium when I didn't ask for and didn't agree to that, then that's on you, and I thank you for the donation. All right, but back to the filling. We now have 143 bar of helium in our cylinder, and we want to get to our 1065 fill. Now, easiest is to now put the oxygen in. So we now need to add in 0.270 moles of oxygen. But that's difficult because we're now starting to mix a different trimix, or rather heliox in this case. If we're adding the 0.270 moles of oxygen to the 5.240 moles per liter of helium, then this is actually 5% of the total number of molecules. So we're looking at a final mix of 595. And if we put a 595 into our van der Waals, then, well, we need to compute the A and B for 595 first, and then solve for 5.24 plus 0.27, whatever the sum of those is, moles of 595. What pressure will that give us? Well, that gives us a pressure of 151 bar. We already had 143 of helium, so we stop filling at 151, which means we need to add 8 bar of pure O2 to the cylinder to get us the 151 bar of 595. And finally, we can fill the rest up with air to 232, which gives us the final 1065 mix. Again, we can cross-check. The air that we're filling is 34.9%. But if we think about the 1065 one with the ideal gas law, then we would only expect to fill 31.6%. So here, the amount of oxygen and nitrogen would be a little bit less. Is that a problem? Maybe. Now, 1065 is already hypoxic, so anyone diving this is going to be hypoxic qualified. They can deal with this. But if we're looking at a normoxic mix and we're asking for a 18% oxygen value, and you're giving me a 16% because you're a couple percent below, technically someone who's normoxic qualified may not be allowed to dive that mix, so a remix has to be done. Similarly, if we think about something like a nitrox mix, I mean, we're looking at 4% difference here. If we were to relate this to a standard recreational mix, say 36%, plus minus 4%, well, if we're looking at a 40%, that might be too rich for the dive that we want to do. If we're looking at a 32%, we might not be happy with that either. I mean, usually we would reject plus minus a percent, and here we're looking at 4% fluctuations. A blender using the ideal gas law, therefore, would not be a happy camper with loads and loads of cylinders being rejected for not being filled to the right gas. All right, so what does that mean in conclusion? Well, we've seen that there are some effects or there are some circumstances where we don't need to bother. If we're doing gas planning with 200 to 232 bar cylinders, then we're basically unaffected. I mean, at the end of the day, this is roughly the range where the two predictions, at least for air, coincide. Other gases that are usually used in recreational diving aren't going to be far off because they're just slightly enriched air. If we're looking at a pressure below 200 bar, i.e., we're part way along our dive, and we're trying to figure out how much gas do we have from reading an SPG value, then we've seen that we're actually underestimating the amount of gas that we have. So we're adding conservatism to our dive planning and to our decision making processes. So that's a good thing to do. For recreational diving, don't think we really need to bother. Now, if we're looking at 300 bar cylinders, then we kind of do need to bother, as a 300 bar cylinder with air really only has roughly 90% of the gas available that the ideal gas law would predict. Now, I do have 300 bar cylinders, and I have to admit I never use van der Waals to actually do the computation. Instead, what I do is I do my ideal gas law computation and I subtract 10% of whatever my gas prediction is. So I'm actually using the fact that we have a little bit more than 90% of what the ideal gas law prediction is. I go down to 90% to give myself a little bit of additional buffer, and that's how I do my gas planning. But I do take van der Waals into account when I do gas planning at this stage. And if you are doing gas planning in the sense of how much bailout do I have, i.e., how far can I go, how much deco can I do in case of lost deco or similar things, then these kind of effects are becoming quite important. And I would urge anyone using 300 bar cylinders to actually start taking van der Waals into account, whether this is by exactly using van der Waals equation or by using a rule of thumb like 90% of the prediction is roughly what I have. Finally, if you are a gas blender, then absolutely you're going to have to bother, because if you're blending gas and you're not taking it into account, you're going to be way off with your gas blending. So any gas blending software should give you the van der Waals prediction, not the ideal gas law predictions. And if we think about realistic gas blending, where we may have a cylinder with already some gas in there, then how much gas do we drain before we put helium and oxygen in and then an air top? That's becoming even more difficult than the example that we went through. So, do we need to bother? Well, depends on what you're doing. Standard recreational diving? No, not really, and I'm pretty sure that's also why the dive agencies never talk about this. 300 bar cylinders, I would say we should bother, and this is something where I think diving agencies should start talking about this kind of stuff, especially when we are talking about different cylinders and what kind of equipment is available and the impact that has on our diving. And if you're going back gas blending, then 100% do care, or I care. I hope that was interesting to people. Hope you learned something. Have a good one, and see you guys next time. Bye bye.